So, if you take a machine that weighs, well, more than the entire Eiffel Tower, right? And you swing an 80-ton bucket of solid rock just dozens of meters off its side, like way out into thin air.
Yeah, out over absolutely nothing.
Exactly. I mean, it just shouldn't stay upright. By every intuitive law of physics that our brains actually understand, that machine should just violently, catastrophically rip itself right out of the earth and collapse.
It really should just be a crumpled mountain of steel. I mean, the forces involved there are so massive that your brain just automatically assumes gravity is going to win that fight instantly.
Right. Gravity always wins. Yet, out in the mines of Germany, it doesn't. Today, we are looking at the Bagger 293, which currently holds the title of the largest land vehicle ever built.
It's an absolute monster of a machine.
It really is. And our mission for today's deep dive is to basically explore the invisible physics, the, hyper-calculated engineering, and the absolutely razor-thin margins of error that keep the world's largest land vehicles from completely destroying themselves.
Because honestly, whether you're a dedicated engineering nerd or you're just someone who occasionally walks past a downtown construction site on your way to get a coffee,
Yeah.
this is going to completely change how you view these massive machines.
Oh, 100%. We're uncovering the hidden systems preventing disaster every single second these machines are turned on.
And to really grasp what is at stake here, you have to understand the sheer scale of the Bagger 293. Like, it is a structure so massive, it literally creates its own horizon line when you stand next to it.
Which is just wild to even picture.
Right. We're talking about a machine that weighs over 14,200 metric tons. It's 220 meters long, and it stands 96 meters tall.
So it's basically a moving skyscraper. And the focal point of this this mechanical Leviathan is its excavation wheel. This wheel alone is 21.6 meters in diameter.
Which is basically a 7-story office building, just spinning.
Yeah, a spinning building. And attached to that wheel are these massive buckets. A single one of those buckets scoops up over 100 cubic meters of material at a time. I mean, this thing is chewing through up to 240,000 cubic meters of earth every single day.
The scale is just relentless.
It is. But here is the core anomaly that we really need to talk about. When this colossal machine swings its boom arms sideways, extending dozens of meters out from its main body, scooping up 80 tons of rock and dirt in one go, nothing happens to the machine itself.
Right, it doesn't lean a fraction of a degree. It doesn't shift. It's just completely static.
I mean, I try to visualize having a 500-ton boom arm reaching out into thin air, holding 80 tons of rock suspended over ground that the machine isn't even standing on. Like, how does that not just tear the machine in half or instantly tip it over?
Well, to answer that, we basically have to unlearn almost everything we naturally assume about heavy objects. We are so wired to think that heavy things just stay put because they're heavy.
Right, heavy means stable in our minds.
Exactly. But we're ignoring the basic, unrelenting physics problem at play here, which is the law of torque.
Okay, let's unpack this for the listener. I think the source had this really great analogy about a child pushing a large box, right?
Yeah, that's a perfect way to visualize it.
Yeah.
If a child pushes a heavy box right at the base, it's really hard to move. But if they push the very top edge, they can tip it over pretty easily.
Right, because they are increasing the distance from the pivot point at the bottom, which increases the torque. Let's make this even more tangible. Imagine holding a 10-pound bowling ball.
Okay, I'm picturing it.
If you hold that bowling ball tight against your chest, it's pretty easy to stand there. Like, you could probably hold it there for an hour. But now, take that exact same 10-pound bowling ball and hold it out in front of you with a completely locked, straight arm.
Oh, your shoulder will be screaming in about 2 minutes.
Exactly. The ball didn't suddenly gain mass. It still weighs exactly 10 pounds. But by extending it away from your center of gravity, you've drastically increased the torque.
Right. Torque is that rotational force that's actively trying to pull your arm down. It increases not just with weight, but with distance.
So if you take that locked arm holding a bowling ball and you scale it up to the size of a skyscraper, you have a 500-ton boom extending outward, and then you add an 80-ton load of rock at the very end of it.
The tipping force, the torque acting on the base of that machine, becomes absolutely enormous. It is generating a catastrophic rotational force every single time that arm swings out to dig.
Which means the earth under the front of the machine is experiencing this concentrated, immense pushing force, while the back of the machine is actually experiencing a lifting force, like the machine is acting like a giant lever trying to pry itself off the ground.
That's exactly what's happening. The front is being crushed down, and the back wants to lift up.
Wait, I have to stop you there because this leads to the most natural assumption I think anyone makes when looking at this. I mean, I understand torque, but if the machine weighs 14,200 tons and the rock at the end of the arm only weighs 80 tons, isn't that just a brute force win for the machine?
You'd think so, right?
Yeah. Shouldn't the sheer...
Not at all. Think about the Eiffel Tower, since we used that for scale earlier. It weighs thousands of tons. But if you were to magically tilt the Eiffel Tower far enough so that its center of mass moved just 1 inch outside the boundary of its four legs, it doesn't matter how many thousands of tons it weighs.
They're going down.
It will fall over. Gravity is no longer pulling it straight down into its supports. Gravity is now pulling it past its supports. You cannot cheat the physics of torque just by throwing more total mass at the problem.
Okay, I hear that, but what about the tracks? Like, I look at the Bagger 293, and it doesn't move on standard wheels. It moves on these sprawling, massive crawler tracks.
Right, the crawler assemblies. They're huge.
Yeah, each track unit weighs hundreds of tons on its own, and they are incredibly wide. So if I stand on a moving subway train with my feet squeezed tightly together, I'm going to fall over the second the train lurches.
For sure, you have no base.
But if I spread my legs wide and widen my base, I'm perfectly stable. Don't the massive tracks on this excavator do the exact same thing? Just give it a super wide base.
Well, that subway analogy is actually perfect for explaining why you're still vulnerable. Yes, spreading your feet on the subway makes you more stable. But does it make you completely immune to falling over?
Well, no, I guess not.
Right. If the train slams on its emergency brakes hard enough, you are still going down no matter how wide your stance is. All a wide track does for an excavator is extend the tipping boundary.
Expand on that a bit. What do you mean by the tipping boundary?
It basically takes the line on the ground that the machine would tip over and pushes it further outward.
Ah, okay, so it's just moving the goalposts. It's giving you a wider buffer, but the cliff edge is still there.
Exactly. The physical laws of torque and center of mass still exist unchanged. The wider tracks just mean the machine has to reach a little bit further out with its boom arm to trigger the tip.
It just delays the inevitable.
Yes. It doesn't solve the underlying physical vulnerability of the lever. It merely delays it. And when you're dealing with a boom arm that can reach out the length of a football field, you can easily outreach the bucker provided by those tracks.
That is fascinating. So brute force mass doesn't save you, and giant wide tracks don't save you. Which means that stability isn't a passive trait.
Not at all.
It isn't just something that happens naturally because the machine is big and heavy. Stability has to be an intentional, highly active design choice. Like, engineers have to figure out a way to actively manage where the center of gravity sits every single millisecond the machine is operating.
And they accomplish this through an incredibly dynamic system.
Yeah.
The most visible part of that system, the first active pillar, really is the counterweight.
Right, the giant block on the back.
Exactly. If you look at virtually any excavator, from a small one digging a trench on your street to the giant mining behemoths, you will see a massive, dense block at the very rear of the rotating structure.
Usually made of solid cast iron or stacked steel plates, right?
Yes. And the sheer scale of these blocks is staggering. Depending on the machine, that counterweight can make up 10 to 15% of the vehicle's entire operating weight.
Wow. So on a massive machine, you might have hundreds or even over 1,000 tons of just dead, solid iron hanging off the back.
Its function is elegant in its simplicity, really. It creates a rotational force in the exact opposite direction of the load being lifted at the front.
Oh, I see. So it's literally fighting the arm.
Exactly. When that boom extends forward and picks up a massive scoop of earth, it generates a massive forward tipping torque. Simultaneously, that chunk of cast iron at the back is generating a rearward tipping torque.
Like two kids on a seesaw.
Perfect analogy.
Yeah.
As long as those two rotational forces balance each other out, the upper structure of the machine stays perfectly flat.
Okay, I have to challenge this, though, because it seems like there's an obvious, foolproof solution staring us right in the face here.
Let's hear it.
If a tip-over is so catastrophic and the entire goal is to counterbalance the front, why not just make the counterweights ridiculously huge? Like, make them 50% of the machine's weight. Put 5,000 tons of iron on the back so it literally never tips forward under any possible circumstance.
That's a great question. But the problem is the machine still has to exist in the real world. In engineering, every single solution introduces a new stress point. It's just a relentless game of optimization trade-offs.
So making it heavier breaks something else.
Think about the physical structure of the machine. If you hang 5,000 tons of dead weight off the rear chassis, you are placing immense continuous stress on the steel skeleton of the machine. You run the risk of the machine literally snapping its own back when the front bucket is empty.
Oh. Oh, because when the bucket is empty, there is nothing pulling forward to counteract the massive weight pulling backward.
Precisely. You would create a machine that tips over backwards the second it drops its load.
That makes total sense. I didn't even think about the empty bucket scenario.
But even beyond that, every single kilogram you add to that counterweight increases the total weight pressing down on the crawler tracks. You drastically increase the ground pressure.
And the ground can only take so much.
Right. The soil under the machine can only hold so much weight per square inch. If you over-engineer the rear weight, you might stop it from tipping forward, but you will cause the entire machine to sink straight down into the mud and become completely immobilized.
Which means the counterweight has to be perfectly dialed in. It has to be just heavy enough to stop the tipping, but light enough to not snap the chassis or sink the machine.
It's a very fine line.
But here's the problem. A counterweight is a fixed, solid block of iron. Its weight never changes, but the load at the front of the machine is constantly changing. The arm is reaching out, pulling back, dropping dirt, picking up dirt. The math is totally dynamic. So how does a static block of iron balance a dynamic, moving load?
Well, it doesn't do it alone. The counterweight is just one part of the equation. The second pillar is geometry control. The physical shape of the machine dictates the physics.
Geometry control. Okay, break that down for me.
So the boom, the arm, the hydraulic cylinders, the bucket, these specific angles between all these massive moving parts dictate exactly how far the load center of mass is displaced from the tipping axis at any given second.
The engineers refer to this as the working envelope, right?
Yes, the working envelope is the full, three-dimensional range of positions that the bucket can safely reach. Engineers calculate the exact tipping forces for every possible point within that envelope, comparing it against the machine's structural capacity and its specific counterweight.
So the operators sitting in the cab aren't just out there winging it. Like, they aren't pulling levers and going by the seat of their pants, guessing how far they can reach before things feel wobbly?
Absolutely not. They are constrained by load charts.
Load charts, okay.
Historically, load charts were literal thick, laminated binders sitting in the cab. Today, they are integrated into onboard computer systems. But the principle is exactly the same. They define strict mathematical boundaries.
Give me an example of how that looks in practice.
Sure. The chart dictates that if you are reaching exactly 12 meters out at an angle of 45 degrees, you can lift exactly this many tons. If you reach out to 15 meters, that allowable tonnage drops significantly.
Because extending the arm increases the torque, even if the weight in the bucket stays exactly the same.
Exactly. And if an operator ignores those numbers and exceeds the limit, they might not instantly tip the machine over because there are built-in safety margins, but they are actively erasing that safety margin.
They're eating into their own buffer.
Yeah. They are intentionally driving the machine into a physical gray zone where stability is no longer guaranteed by the mathematics.
And we also have to talk about where this math is actually grounded, because torque needs a pivot point. There has to be a literal edge of the cliff, which brings us to the third pillar.
Right, the support footprint. For a tipping axis to exist, there must be a defined boundary line on the Earth. On the giant mining machines, like the bagger, that edge is defined by the outermost edge of the crawler tracks.
But it's different for smaller machines, right?
Yeah, on smaller construction excavators or the cranes you see building high-rises, it is often defined by outriggers.
For the listener, outriggers are those massive mechanical legs you see extending out from the sides of a crane or an excavator, pushing heavy steel pads down onto the dirt or the asphalt.
And what those outriggers do is artificially manipulate the support footprint. When you push those legs down, you actually lift the tires or the tracks slightly off the ground.
Oh, so the tracks aren't even touching the ground anymore.
Right, the weight transfers to the outriggers. By doing that, you shift the tipping axis away from the narrow body of the vehicle and push it all the way out to those wide steel pads. You can sometimes double the effective stability base of the machine in a matter of seconds.
That's incredible. So to keep this machine from destroying itself, you have this constant tug of war. You have the counterweight pulling back, you have the specific geometry of the arm controlling how far forward the load pushes, and you have the tracks or outriggers deciding where the pivot point actually sits on the earth.
And the crucial takeaway, what's fascinating here, is that none of these systems can function in isolation.
They all have to work together.
The stability of a crane or a massive bucket wheel excavator relies on a real-time, continuous symphony of all three. If the counterweight is wrong, if the arm extends too far, or if the outrigger shifts, the entire symphony collapses.
This brings us to a concept that completely blew my mind when going through our research. I want to bring you, the listener, into the actual invisible mathematics happening inside the steel while this machine is working, because we need to redefine what the word stability actually means.
It's a huge paradigm shift.
Most of us think of stability as a binary state, like a light switch. It's either on or off.
Yeah, we view it as an absolute. The glass of water is sitting on the table, or the glass of water is falling off the table.
Right. But for an excavator, stability is not a binary state. It exists on a sliding continuum. Think about the coffee cup sitting on your desk right now. If you push the rim of that cup and tilt it just 10 degrees, it doesn't fall over.
It just tips slightly.
And when you let go, it rocks back down flat onto its base. That ability to rock back is what engineers call a restoring moment. The Bagger 293 is doing the exact same thing your coffee cup is doing, just with 13,000 tons of steel.
That's a great way to picture it.
Stability is a constantly shifting ratio between two distinct mathematical values, the tipping moment and the restoring moment.
And this is where we have to clarify a term that engineers use constantly, the ton meter. It sounds like jargon, but it is actually highly intuitive. Because torque is a rotational force. You can't measure it just in tons, and you can't measure it just in meters.
You have to combine them.
Right. You have to multiply the weight by the distance.
Let's walk through a tangible example of this invisible tug of war step by step. Let's start with the forward pull, the tipping moment.
Okay, sounds good.
Imagine our machine is lifting 50 tons of dirt, and the arm is reaching out horizontally exactly 10 meters away from the front edge of the tracks. You take the 50 tons, multiply it by the 10 meters of distance, and you get a tipping moment of 500 ton meters.
Perfect. That 500 ton meters is the aggressive, invisible force actively trying to drag the front of the machine down into the dirt.
Okay, so how do we calculate the pushback?
Now, to counter that, the machine calculates its restoring moment. It takes its own weight. Let's simplify and say it has 300 tons of engine block and counterweight sitting at the back. And let's say the center of that weight is sitting 3 meters behind the tipping edge.
Okay, 300 tons, 3 meters back.
300 tons multiplied by 3 meters equals a restoring moment of 900 ton meters.
Okay, so we have a forward rotational force of 500 ton meters and a backward rotational force of 900 ton meters. 900 is greater than 500. The math holds. The machine is mathematically stable.
It has a safety margin of 400 ton meters. But here is where the danger lies. That margin is highly sensitive to the operator's actions.
Right, because things are always moving.
If the operator decides they need to dump that dirt just a little bit further away, and they extend the boom from 10 meters to 15 meters, well, the weight in the bucket didn't change. It is still 50 tons. But 50 tons multiplied by 15 meters suddenly generates a tipping moment of 750 ton meters.
Wow. Your safety margin just evaporated from 400 down to 150 just by reaching out a few more meters.
And what happens if the operator loses focus or ignores the load chart and reaches out to exactly 18 meters? 50 tons multiplied by 18 meters is 900 ton meters of tipping force.
And your restoring moment holding the machine down is exactly 900 ton meters. So they perfectly match.
The tipping moment now perfectly equals the restoring moment. This is what engineers call the absolute tipping point. It is not a metaphor. It is the literal mathematical threshold where the forces perfectly cancel each other out.
Here's where it gets really interesting. What happens physically to the machine at that exact second? Because it sounds terrifying.
It is. The phenomenon is known as zero ground reaction.
This is the massive aha moment for me in all of this. Explain what zero ground reaction actually feels like physically.
When the forward force perfectly equals the backward force, the rear of the machine is no longer pressing down on the earth. The ground reaction drops to zero. The rear tracks, or the rear outriggers, are completely weightless.
Meaning the back end of a multi-thousand-ton machine is literally hovering.
It might be floating a single millimeter above the dirt. It is perfectly balanced on a single microscopic line at the front edge of the front tracks. The machine has become a seesaw, perfectly balanced in the center.
Just picturing that. A machine the size of a skyscraper making that deafening roar of diesel engines and grinding gears, and yet the back half of it is weightless, like you could slide a piece of paper under the rear tracks.
And here's why that is the most dangerous state in engineering. If the operator extends that arm even one single millimeter further, or if a single heavy rock tumbles into the bucket, The tipping moment exceeds 900.
The balance is broken.
The balance is gone. The center of mass crosses the tipping axis.
Can the operator feel this happening? Like, can they just slam the joystick in reverse and pull the arm back to save it?
In almost all catastrophic cases, no. Because of the incredible mass involved, the acceleration once it passes that point is absolute. Gravity takes over entirely.
Oh, it's just a runaway train at that point?
It becomes a runaway physical reaction. When thousands of tons of steel begin to fall, no hydraulic cylinder on Earth is fast enough or strong enough to pull it back. The machine is going to the ground, and there's absolutely no recovery.
Which is deeply unsettling. But, if you look at the math on paper, as long as the restoring moment is larger than the tipping moment, we are safe. 900 beats 500, we win.
On paper, yes.
But these machines do not work on graph paper. They do not operate in a vacuum. They work in dirt, in mud, in freezing rain, and in highly dynamic, chaotic environments.
Which is where the pure physics collides with geology. The math we just discussed fundamentally assumes a solid, rigid, unchanging surface beneath the machine. But out in the real world, whether it's the lignite mines of Germany or a downtown high-rise project, the surface is the ultimate unpredictable variable.
Let's talk about lignite, actually, because that's where the Bagger 293 works. Our source notes that lignite isn't like mining through solid granite. Lignite is a very soft, crumbly, brown coal.
Very soft.
And to get to it, these machines have to strip away the overburden, which is the millions of tons of loose dirt, clay, and rock sitting on top of the coal. It is inherently unstable ground.
And that instability ruins the clean mathematics. Think about how a machine's weight is distributed. If you park a massive excavator on a perfectly flat, solid concrete, the tracks distribute the weight evenly across every square inch.
Right, it's totally uniform.
The tipping axis is a perfectly straight, predictable line. But what happens if you park that same machine on a layer of wet clay or loose gravel?
The ground isn't going to push back evenly.
Exactly. The front left corner of the track might sink 2 inches into a soft pocket of mud, while the back right corner sits on a hard slab of buried rock. In an instant, you have unintentionally shifted the machine's effective center of gravity. It leans.
You've tilted the entire mathematical equation. Like, a machine that was perfectly stable and operating well within its safety margins on level ground can suddenly approach the brink of tipping over simply because the dirt beneath one corner of the track got wet.
This unpredictable nature of dirt is exactly why you see these giant mining excavators operating what the industry calls prepared benches.
Prepared benches, what are those?
Engineers know they cannot trust natural random terrain. So before the massive bucket wheel excavator even arrives, other machines carve out massive, perfectly leveled platforms benches into the side of the mine.
So they terraform the area first?
Yes. The earth is compacted and tested. The excavator only travels along these highly precise, engineered paths designed to keep the operating angles strictly within a fraction of a degree.
They basically have to build a temporary highway out of dirt just to let the machine do its job safely.
And if the machine deviates from that prepared angle, it deviates from its safety envelope.
But smaller construction excavators, or even massive crawler cranes working on a hillside, they don't have the luxury of a perfectly prepared bench. They are working on hills, near the edges of trenches, on totally uneven terrain.
Which is much riskier.
Which brings us to how these things actually fail in the real world. When we see a viral video of a crane collapsing or an excavator tumbling into a pit, how does the math actually break down? And the number one cause, the most terrifying failure mode, according to our deep dive here, is ground collapse.
To understand ground collapse, we have to talk about what dirt actually is. Soil is not solid matter. It is a matrix of millions of tiny rock particles with air and water trapped between those particles.
It's like a sponge made of rocks.
Pretty much. When an engineer calculates the stability of an excavator, they rely on a metric called ground-bearing capacity. They calculate exactly how much downward force the soil can handle before the particles shear apart.
But in a mining environment or a construction site, you have explosives creating blast zones that fracture the rock. You have torrential rain saturating the soil with water.
And this introduces a phenomenon known as soil liquefaction. When millions of pounds of force from an excavator's track press down on highly saturated soil, the pressure of the water trapped between the dirt particles spikes dramatically.
Oh, because the water has nowhere to go.
Right. If the water cannot escape fast enough, the water pressure actually pushes the dirt particles apart. The soil loses all of its internal friction.
It literally stops acting like a solid and begins to behave like a liquid.
Yes. And if the soil directly beneath the front tipping edge of the track suddenly liquefies, which can happen in literal milliseconds, the effective support footprint simply
It
vanishes.
just disappears.
The solid line on the ground that your math was relying on as a pivot point is gone. It's like pulling the rug out from under the math.
And the terror of that is the speed. If one track sinks even 6 inches into a pocket of liquefied soil, the sheer momentum of 14,000 tons tilting forward pulls the machine past the point of no return before the operator can even blink, let alone react.
It is the most insidious type of failure because it breeds a false sense of security. The operator could be doing everything perfectly. They could be reading the load chart, managing the geometry, holding the load close to the machine.
They could be checking all the boxes.
Exactly. The math inside the cab was 100% correct, but the ground lied to the math.
That is wild. Okay, what about slopes? Because our research notes that traveling on uneven ground is one of the most common causes of tipping for standard construction excavators, like not just soft dirt, but actual hills.
This comes entirely back to the center of gravity and lateral forces. When an excavator drives straight up a hill, or straight down a hill, its center of mass remains relatively aligned between the two tracks. It is surprisingly stable.
So forward and backward is okay.
Usually, yes. But the danger occurs when the machine travels across a slope, moving horizontally, perpendicular to the fall line of the hill.
Imagine walking horizontally across a really steep ski slope. Your boots are biting into the snow, but your entire body weight wants to pull you down sideways, tumbling down the mountain.
Exactly. When a tall, heavy machine drives across a slope, its center of gravity shifts laterally toward the downhill track. Every machine has a strictly rated side slope capacity, a maximum angle it can traverse.
And if you push past that angle,
If the angle of the hill exceeds that rating, or if the downhill track slips on loose gravel, the center of gravity crosses the boundary of the downhill track. The torque pulls the machine over sideways. And because these machines are so top-heavy with their massive boom arms and upper structures, a lateral tip happens incredibly fast.
which brings us to the final major factor in these disasters. And this one is perhaps the most frustrating because it doesn't involve complex geology or invisible soil mechanics. It is entirely preventable. We have to talk about overloading and the human element.
We established earlier that load charts are strict, unforgiving mathematical boundaries. They are not conservative estimates. They are not gentle suggestions from the manufacturer.
They're absolute limits.
They are the absolute, calculated limits of the physical materials.
But the entire concept of a load chart relies on the operator knowing exactly how much weight they have just scooped into the bucket. And the source highlights a deeply dangerous, very common scenario: digging blind, lifting buried material where you cannot see the density of what you are pulling up.
When an operator is digging through loose, dry topsoil, they develop an intuitive feel for it. They know roughly what a full bucket of dry dirt weighs, but geology is rarely uniform.
It's constantly changing.
Imagine the operator is swinging the bucket through the earth, and instead of dry dirt, the teeth of the bucket bite into a dense, hidden pocket of wet, compacted clay. Or they catch the edge of a massive, buried slab of concrete from an old foundation.
The operator looks at the bucket and assumes, okay, I have a standard load, probably 50 tons, but because the material is drastically denser, they are actually holding 80 tons.
And instantly, the tipping moment spikes astronomically. The mathematical margin of safety drops to zero. There are no warning bells ringing in the air. There are no visual cues that the dirt is heavier. The machine doesn't groan any louder just instantly. The operator gets the density wrong, and a multi-million-dollar machine is crossing the threshold of zero grand reaction.
Now, to be fair to the engineers and the operators, it's not the 1970s anymore. Modern machines use incredible technological safeguards to try and prevent human error.
The Bagger 293 and almost all modern hydraulic cranes and excavators are outfitted with sophisticated real-time load monitoring systems. These are networks of sensors placed along the boom, the hydraulic cylinders, and the chassis.
So it's constantly measuring everything.
Yes, they measured the actual physical forces, the literal stress and strain on the steel millisecond by millisecond.
Our source mentions automatic alarms that sound in the cab, and even physical load limiters. Systems that will literally cut the hydraulic power and physically prevent the operator from pushing the joystick any further if the computer detects the tipping moment is getting too high.
They are brilliant systems.
Yeah.
They really are. But this raises an important question that every engineer has to reckon with. Do these computers, these sensors, and these alarms actually replace the physics?
No, they don't change the gravity.
Exactly. They merely make the invisible physics visible to the human eye. They translate invisible torque in restoring moments into a glowing screen and a warning buzzer in the cab. But if the operator chooses to override the buzzer, or if the soil suddenly liquefies beneath the sensors, the physics will still take the machine down.
So the technology is just an interpreter. Physics remains the executioner.
Beautifully said.
So, after digging through all of these sources, all of this intense math and geology, what does this all actually mean? We started this deep dive looking at a machine the size of a skyscraper, the Bagger 293, and asking a very simple childlike question. Why doesn't it tip over?
It's the core question.
And I think the overarching revelation here is a profound philosophical shift in how we have to view these machines. Stability is not a magical property built into the steel at the factory. It is not an inherent permanent trait.
Not at all.
Stability is a precarious, fragile state. It is a condition that the machine is actively, violently being kept in by calculated design, strict procedure, and utterly unforgiving physics.
It is an active performance, not a passive state of being. Every second that machine operates, the counterweights are pulling back with immense force. The geometry is constantly shifting the center of gravity, and the footprint is constantly redefining the edge of survival.
It's a high-wire act.
It really is. It is a high-wire balancing act being performed with thousands of tons of metal 24 hours a day, 7 days a week.
And I think the real relevance to you, the listener, is how this changes your perspective of the built world around you. Like the next time you drive past a highway expansion, or you see an excavator digging a deep trench for a water main, or you look up and see a towering crane reaching into the skyline to drop a beam on a new apartment building.
You'll see it totally differently.
You aren't just going to see a big, slow, heavy vehicle making a lot of noise. You are going to see an incredibly tense, real-time mathematical equation unfolding right in front of your eyes. You will see the invisible forces of torque actively trying to rip that machine down into the street, and the silent, massive chunks of cast iron counterweights fighting back.
You'll realize that the machine isn't just resting peacefully on the ground. It is actively negotiating with gravity, and the margin of victory between a successful lift and a catastrophic collapse is sometimes just a few decimal points on a digital load chart.
To wrap this up, I want to leave you with a final provocative thought. A concept drawn directly from the deeply unsettling conclusion of our research material today. We spent time talking about that exact terrifying moment when a machine reaches its tipping point.
The zero ground reaction.
Exactly. The exact millisecond where the tipping moment equals the restoring moment. The moment of zero ground reaction where the rear tracks lift a single millimeter off the ground.
At that exact second, all 14,200 tons of the Bagger 293, every ounce of its steel, every drop of its oil, plus the 80 tons of rock sitting in its bucket, is no longer distributed evenly across those massive, sprawling crawler tracks.
Because the back is floating, millions and millions of pounds of force are suddenly shifting forward. They are concentrating onto a single, microscopic geometric line at the very front tipping edge of the front track. Think about what is happening to the dirt directly underneath that specific line.
It's taking all the weight.
The ground pressure spikes from a manageable load to an unimaginable hyper-concentrated level. It is a level of focused physical trauma that dirt and rock were never meant to withstand.
And that is the ultimate cliffhanger of heavy engineering. At that exact moment of maximum stress, whether the microscopic particles of that soil hold firm and push back, or whether the water pressure spikes and the earth shatters and liquefies under the pressure that dictates the survival of the machine and the operator.
It's all up to the dirt.
It all comes down to the hidden, terrifying physics of soil-bearing capacity.
So the next time you see one of these mechanical giants swinging its massive arm through the sky, defying gravity, just remember, it is never the weight that keeps it safe, it is the math. And the math only works if the dirt decides to cooperate.